right, let's dive into one of the weirdest, most fascinating ideas in all of science, wave-particle duality. It's a concept that completely breaks our everyday understanding of how the world is supposed to work.
So, for literally centuries, the smartest people on the planet were stuck on this one question. What exactly is light? Is it a wave, like a ripple in a pond? Or is it a particle, like a tiny little bullet? Sometimes it seemed to act like one, and other times it acted like the other. It was a contradiction that was about to push physics to its breaking point.
Now, to really get why this was such a huge deal, we have to look at what came before. For a long time, everyone was pretty happy with the classical wave theory of light. It worked, mostly. But a few key experiments just refused to play by the rules, and they started to show a massive crack in the very foundation of physics.
And the conflict was, well, impossible to ignore. The old wave theory said that if you shine a brighter light on something, it should knock out electrons with more energy. Makes sense, right? More intense light, more power. But that's not what happened. Experiments showed the energy of the electrons depended on the light's color, its frequency. And the old theory also said there should be a delay, a little bit of time before the electrons pop out. But in reality, it was instant. The whole thing just didn't add up.
We're not talking about small little rounding errors here. These were fundamental failures. The rulebook that physicists had been using for centuries just didn't work anymore. Something new was needed, and fast. And this is where the story gets really good. Enter a young Albert Einstein in 1905. He looked at this mess, and he didn't just try to patch up the old theory. Oh no, he proposed something so radical it would change everything. Einstein basically said, what if light isn't a continuous wave at all? What if it's actually made of tiny individual packets of energy, like a stream of microscopic energy bullets? He called these packets photons. And here's the key. Each photon's energy wasn't based on brightness, but on its frequency, its color.
This wild idea perfectly explains something called the photoelectric effect. See, in this device, a photocell, you shine light on a metal plate. If a single photon has enough energy, enough of a punch, it can literally knock an electron right off the surface. It's like a one-on-one collision.
And he even came up with the math to prove it. This equation shows that the energy of that ejected electron depends directly on the photon's frequency. A higher frequency photon, like from blue light, delivers a much bigger kick than a lower frequency one from red light. Suddenly, all those confusing experimental results made perfect sense.
So, Einstein proved that a wave, light, can act like a particle. That's already pretty mind-bending. But it got a young physicist named Louis de Broglie thinking, and he asked an even crazier question. If waves can be particles, could particles also be waves?
De Broglie's idea was just beautiful in its simplicity. He believed nature loves symmetry. So he thought, if light gets to have this weird dual personality, then matter, electrons, protons, you, me, everything must have one too. It was an idea so out there it was almost science fiction.
And he didn't just stop with the idea, he wrote down the math for it. De Broglie proposed that you could calculate the wavelength of any object, which he called lambda, by dividing a constant h by the object's momentum. Think about what that means. Everything that moves has a wavelength. You have a wavelength, a car has a wavelength, the Earth has a wavelength.
Okay, so you're probably wondering, why don't I see a baseball ripple as it flies through the air? And that's a great question. It's because this wave effect is only really noticeable for super tiny things moving really fast. For something as massive as a baseball, the wavelength is so ridiculously small that we could never ever hope to detect it. But for a tiny little electron, well, that's a whole different story.
But a bold hypothesis like that needs some serious proof. So in 1927, two physicists, Davison and Germer, they put together an experiment to test de Broglie's idea once and for all. Could an electron, a particle, really act like a wave?
So let's take a look at what they built. It's really clever. You've got an electron gun over here which shoots a stream of electrons. They aim that beam at a carefully prepared crystal of nickel. And then they have this detector that can swing around and measure exactly where the electrons go after they hit the crystal. So here's the play-by-play. The gun fires electrons. They zip over and hit the nickel crystal. Now the atoms inside that crystal are arranged in a perfect grid, which acts like a bunch of incredibly tiny slits. The detector then moves around to count how many electrons scatter at different angles. Now, if electrons were just simple particles, you'd expect them to just bounce off kind of randomly, right? Well, that is not what happened at all.
The result was stunning. The detector found a clear pattern of peaks and troughs, an interference pattern. And that is the definitive fingerprint of a wave. The electrons were diffracting off the atoms. It was unbelievable. De Broglie was right. Matter is a wave.
So let's just take a moment to put this all together. From light acting like a particle to particles acting like waves, physics had been completely turned on its head. And all of this leads us to our new, very strange, and incredibly profound understanding of how the universe actually works.
And this is the main takeaway, the crucial idea right here. It's not that things are either a wave or a particle. It's that everything, from a photon of light to an electron to you and me, has both wave properties and particle properties at the exact same time. Which one you happen to see just depends on how you measure it. This is the core principle of wave-particle duality.
And that leaves us with this final, massive question. If the fundamental building blocks of our universe behave in this bizarre, counterintuitive way, flickering between wave and particle depending on how we look, then what does that say about the solid, predictable world we experience every day? What is the true nature of reality?